2018 Cup Churn Challenge, which placed first out of 575 teams. Real quick about me, I've been in the field of analytics for about 10 years and currently work as the Manager of Business Intelligence at Texas Wesleyan University, and I also have a part-time data science consulting practice. I've been in the field of analytics about 10 years, and I'm a longtime Kaggle competitor, first joined up in 2013, and have entered about 14 Kaggle competitions, including a prize win in 2013, and at one time was ranked in the top 100 Kaggle competitors in the world, achieving Kaggle Master, and took a few years out off of Kaggle, and then recently returned for this competition. Had a little bit of time, free time to dedicate to it, and decided to enter. So, brief overview of the competition. The overarching goal was to use historical subscriber data from KKBox to predict future customer churn on a given test set, which was March 2017. And KKBox is a music subscription service based out of Asia, so all the data related to subscriptions. The target of the competition was to predict the likelihood of customer churn for the upcoming month, and this was defined as true if a subscriber does not renew within the prediction month, which is the month following the current month. Therefore, only members with a subscription expiring in the current month were considered for prediction in a given month. And this was derived from the transactions data set. So, for example, a subscriber that's on a 6-month plan and subscribed 3 months ago is not going to be part of this month's data set because they're not expiring this month. And the evaluation used that was chosen by the competition admins was log loss, so a very common metric, very common in a lot of Kaggle competitions, and nothing too tricky about it. And of note is, as with most data science competitions sponsored by Kaggle, computation time was not a considered factor. Therefore, any number of features could be used, any number of classifiers. So runtime was not a factor. It was purely based on accuracy of the model, of the submissions. And also, in addition, any toolset could be used, any type of solution. So it's a very open-ended competition. Okay, brief overview of the dataset. The KKBox historical subscription data was delivered to participants in 3 files: transactions, user logs, and member data. Transactions contained historical payment and subscription information, including whether or not the customer was on an auto renewal, when they canceled, that record was stored in that file, pricing data of their subscription, length of subscription, that type of data. User logs covered subscriber activity, daily subscriber activity, such as the total number of unique songs played each day, number of seconds logged in each day, etc. Member data contained demographic information about each subscriber, such as birthday, gender, dates that the member joined the service. And overall, as you can see, user logs was by far the largest of the 3 datasets. So it contained about 400 million records, which amounted to about a 15 to 20 gigabyte raw file, which did create a challenge for a lot of competitors, as that's too much to fit into most desktop clients when we're using simply memory to process, create the model. And overall, there were 22 raw data points across all the files, including 4 date fields. So my approach that I decided to use was, number 1, to focus primarily on utilizing a gradient boosting decision tree based library, because anyone that follows Kaggle knows that those have recently, over the past couple of years, shown a high degree of accuracy. They've been successful in winning a lot of data science competitions. Primarily, they're the XGBoost and LightGBM libraries. And then, secondarily, I was going to ensemble and stack as needed. So that was sort of my approach to the classifier part of the challenge. Secondary to that, I wanted to make sure I carefully handled the temporal aspect of the data. So that meant properly and accurately cross-validating, which is surprisingly sometimes difficult and tricky to do in a temporal-based competition. For example, things like k-fold cross-validation don't work properly. Obviously, you need to account for time factors when establishing your cross-validation sets. And then secondary to that, I wanted to utilize effective techniques for feature engineering that embedded temporal information into the features. And I'll cover some of those techniques in a future slide. And third, because this was such a rich data set with a lot of data points, I thought it was going to be very important to focus on feature engineering and spend the bulk of my time there rather than multi-level stacking, etc. And lastly, due to the large data set size and large amount of feature engineering that I anticipated, I wanted to create a stable, persistent environment for storing the data, the transformations, and those new features. So the tools I landed on that I chose to use for munging and cleaning and loading the data and storing the data, I chose Microsoft SQL Server 2016. And that's because my background, I'm primarily working the Microsoft BI stack, so I'm very familiar with SQL Server, and it was easy to spin up an Azure VM virtual machine that had that pre-installed. So in a few minutes, I could get off and running, loaded the data files into tables, and then proceeded to build T-SQL scripts to clean and munge and join the data and then create features off of that. In addition, used Python and Pandas for secondary cleaning and additional feature engineering. For example, I borrowed some code from past contests that I've used to create features and kind of combined that with my T-SQL features. But primarily about 80% of the feature engineering was done in T-SQL. And then lastly, for the classifiers, again, I used XGBoost and LightGBM libraries implemented in Python. And here's a list of the libraries and package versions that I did use. So for pre-processing and loading, again, I utilized an Azure VM with Microsoft SQL Server environment installed on it. And then that provided a lot of advantages over, I believe, some of the other competitors who simply tried to stay within the Python stack and create just simply in-memory models. Because it eliminated memory and CPU bottlenecks, it gave me persistent storage of my pre-processing steps, and it made it very easy to derive subsets of the data, for example, subsets of the user log file, so that I wasn't processing through all 3 years of data for the majority of my features. It only needed to look back perhaps 60 days. Other pre-processing that I did use that's pretty standard best practice included outlier elimination, imputing nulls and missing values, converting data types. For example, date fields were given to us by the competition admins as an integer, and I converted those into date types for later feature engineering. And then lastly, I did use a provided scala script given by the competition admins to recalculate the churn target label, and that was pretty important, as many of us found out. So for time period splits, basically I split the data into 3 chunks, into 3 time periods. For my training set, I used January, so all the subscribers that had subscriptions expiring in January of 2017. That was my training set. For cross-validation, I used February. And then, of course, the test set, which we were scored on, and our place in the competition was based on, was the March data set. And of note is that, so those time periods were used for determining the prediction window, so the subset of subscribers who we were going to predict churn of. However, the features that were used for predicting that churn were generated off of a lot of other different time windows relative to that prediction time period. So as a quick example, if there's a member with a subscription expiring in January, they're going to fall into the training data set, but we might be looking at their last 6 months of user activity to generate various features, like total songs played each week, etc. And therefore, you can see that there were a lot of relative time windows, but those time period splits I mentioned were just for creating the churn labels. So overall feature engineering had a total of 208 features that I created and tested over the course of 6 to 7 weeks that I created my model. And of those, 76 were used in the final model. Those were derived from all 3 data sources, user logs, transactions, and members data, as well as meta features, which were just sourced from multiple files, and then higher order features, which would be interaction between features. So a quick example of that would be one of the features I had that scored fairly well on the importance chart was a ratio of the number of days since last login and subscription payment plan days of that subscriber. So about greater than 80% of the features were derived from the user logs and transaction files, primarily user logs, especially with about half. And of note, transaction features related to cancellations performed very well and had high importance in the final model. So examples of those were total number of cancellations in a user's transaction history, a Boolean flag describing if their prior month contained a cancellation transaction, and the customer's average cancellations per month. So feature selection, after I'd crafted many of these features, I used a fairly simple iterative loop to one by one iteratively cross-validate score against the February cross-validation set, each field as it was added to the model. And basically, if it increased cross-validation score, then it was added to the model, unless it had a very high correlation found with other existing features. So I just ran a quick Pearson correlation, and if it was extremely high, then I generally dropped the feature, even though it did increase cross-validation score. And then I utilized two distinct methods of creating features from the temporal elements, so I'll go into a little more detail on. So the first I call the relative refactoring method, and this is pretty straightforward, but surprisingly I think overlooked by quite a few of the contestants in the competition. For example, if you do a quick survey of the kernels, which is sample code that's posted by competitors on Kaggle for this contest, you'll see that virtually no one used this method. Everyone sort of fed date-driven features directly into the model with no refactoring at all and no accounting for time periods. So what this method does, again pretty simple, is you're just refactoring features to be relative to the time period which you're modeling. And that allows your time periods to be comparable across different time periods, or your model to be, your different data sets to be comparable across different time periods. And basically what this is doing is it's embedding temporal context into the feature so the model can learn from that. And to accomplish this, again, pretty simple. This is just basically mapping a date-driven feature into a new feature space, which is anchored, which is not anchored at any particular point in time. So you just want it to be relative. So you're just creating a simple numeric feature out of a given data element. So step one, you just select a unit of time measurement most appropriate for a given data element. So in this contest, that was always days. We're not given time of anything, we're only given days. So number two, we chose a consistent point in time within the time period being modeled. So for example, the first day of the month being predicted. So for the training set, that's going to be January 1st, for the cross-validation set, February 1st, etc. And then step three, we create this new feature by taking the difference between the data element of the feature and the selected point in time. So an example of that, to kind of bring that home, if we have a user with a registration date of January 25th and the last login date for that user is January 30th, then using this relative refactoring method, we would create two new features which represent the number of days difference between those two data elements and the start of a given prediction period. So for the training data set, which was that January time frame, we have a days since registration feature, which is going to be 6, so 6 days since they registered on January 25th. And then we have a days since login feature, which is 1, because they last logged in on January 31st, and our relative time that we're using is January 31st. Then for the test data set, those same features are going to be 34 and 29, because assuming no updated activity occurred, it's now been 34 days since they've registered and 29 days since they last logged in. So again, very straightforward, but again, surprisingly kind of skipped over by a lot of practitioners. Second method is the absolute method, and that's even more straightforward. We're simply converting the date field into an ordinal integer and then feeding it directly into the model. So this wasn't necessary, the conversion step was not necessary in the KKbox dataset because they gave us the date fields as integers. And so in general, this method is particularly useful when the absolute date and time contains more signal than the relative date and time. So, for example, if we look at users registration time and we want to capture seasonality of registration time, so for example, if registrations right after holidays have high or low churn behavior, then we want to use the absolute registration date, because no matter what time window we're modeling on, it's important that the absolute registration date is fed in so that we know that it doesn't matter if it was 300 days ago or 200 days ago. What matters is they registered right after a holiday, right? Whereas, of course, the relative refactoring method, what we're doing is we're saying that most of the signal is found in relative days from the given modeling period. So both methods cannot be used together for the same time period, for the same feature, but they can be combined across multiple time period splits. So, for example, registration date in my model, I used both methods on that. So what I did was, if they had registered from January 1st onward, I used the relative refactoring method because basically I was going under the assumption that if someone has recently registered, we want the model to pick up on that, the recentness of that. And then anything prior to January 1st, 2017, I fed in as the absolute method. The idea being that once a certain amount of time has passed, they're no longer a new user, and now what we want to pick up on, what we want the model to see the signal in, is the absolute time of year which they've registered for. And for the absolute method, it can be useful to create more features using parts of the date. So because it's not a relative period of time and it's not just a simple numeric feature, because it is a date time piece, you can do things like create day of year, month of year, day of month, etc. And I did do that with the registration date field. So the top 10 features of the model are listed here, and this is an importance pulled from the XGBoost model. And again, I'll go over it, but my final model was actually an ensemble of LightGBM and XGBoost, but the mostly weighted part of the model was XGBoost, so that's where I pulled my feature importance from. And I won't bother listing off all the features for the sake of time, but one interesting thing to note that you'll see is there was no single dominating feature. So all the feature importance is actually very evenly spread out, which I thought was really interesting. The classifier training and optimization that I used, so again, XGBoost was my primary classifier, and it performed very well. Particularly important was I used the hyperparameter of tree method equals hist, which is basically telling it to use a histogram binning for its tree method growing method, and that basically allowed it to train much quicker. So when I was doing like the iterative cross-validation for all the features I was adding, this trained much more quickly than if you use the other tree growth methods. And of course that was particularly important as the features continued to grow and grow and started to get to 50, 60, and 70. For hyperparameter optimization, I just used simple cross-validation feedback based on, again, that month of February, and that seemed to work just fine. Other learners that I tested were LightGBM, StackNet, and SKLearn's GBM gradient boosting machines. And overall, XGBoost did perform the best. I had interesting feedback from those other learners, but the final model that I did submit that ended up achieving the best score was a weighted average of XGBoost and LightGBM, and those weights were 0.88 and 0.12. and that was basically just a heuristic derived from the competition leaderboard feedback. So the final results, the log loss of the March predictions, the test set, drastically decreased over time. So I have listed here the benchmark all zeros is 1.22. The benchmark prior mean churn rate was 0.176. So those naive benchmarks, you'd say 0.176 was kind of the one to beat. And then XGBoost on just a single feature achieved 0.167. As I added more features, I was able to get it down to 0.104, and that was using no data from the user logs, because I did tackle that last because of the complexity of the size. So just using, I believe, 15 or 20 features derived from transactions in the model data set, or the members data set, sorry. So 17 features total allowed a log loss score of 0.104 on the test set. And then the final model, with all 78 features added, majority user log features, that achieved a 0.07974. And interestingly and thankfully, the cross-validation improvements were correlated almost perfectly with improvements in leaderboard. So that's, of course, very important as you're competing, because I would know that if I achieved an improvement in cross-validation score, then I expected a leaderboard improvement. And if I occasionally did not see the leaderboard improvement I expected, I knew it was probably because I had, introduced a bug into my code and hadn't accounted for something properly. So it was just very nice to have that almost perfect correlation between CV scores and leaderboard. Another thing to note from the results that I found was that trend analysis features were very effective in increasing the accuracy. So you can see once I introduced the user log data, there was a significant drop in log loss. And the way I performed the trend analysis was I had a lot of similar but distinct variations of trends that I fed into the model, just to ensure that it could learn as much as possible from that user activity domain. A lot of various features were used for measuring user activity. So I tested out methods of using sum, mean, max, etc. I ran that on the user's total number of seconds played in the daily average, the number of unique songs played, just number of gross logins, so just any activity on a given day, and then I aggregated all those different things over the various time windows. So prior 2 weeks, user activity, prior month, prior 3 months, ratio of 3 months to 1 month, etc. So in conclusion, I think definitely learned some important things from this competition for me personally. And I think my initial approach was validated, and basically that involved, number one, feature engineering was extremely important. Again, because of the richness of the data set, the number of data points, this high dimensional rich data allowed for, I think, more accuracy to be derived from, so time was better spent on feature engineering versus simply stacking your models and trying to eke out an extra 0.01% of increase. And in general, as I introduced more and more batches of features, I always saw an increase in accuracy. Sometimes not as much as I hoped, sometimes in different areas than I thought, but always there was an increase. I never once spent an evening doing a new batch of features and had it not amount to any increase at all. That didn't occur one time. Second, the methods of dealing with temporal features, while not overly complex, are often overlooked, and associated with that, the details matter, especially when working with temporal data. So you really have to be careful that all the features that you're crafting are properly accounting for those time shifts when you're working with those multiple time windows. And I got caught with that multiple times, where I had not properly modified the code for a given data set. And this is particularly important on high dimensional and high feature count models, because if you're crafting 200 features and most of them are using temporal data, like the user activity, then it's just really important to be very, very detailed with your feature creation and your testing. And lastly, XGBoost, as always, performed extremely well. So acknowledgements, thank you to KKBox for providing such a rich data set. It was really interesting to mine and had a lot of fun with it. Second, thank you to Wisdom 2018 for hosting and providing and sponsoring the competition. And then Kaggle for being such a great competition platform. Really enjoyed it. Thank you.